I welcome all of you to this video. We will show you an integration of a function which has no elementary function, and you could just imagine something like this. How would you integrate this, especially when it comes in the form of a double integral? But let's put this aside. Our culminating event is something with regards to integrating this. But before we do this, we're looking here at reversing the order of integration, so you can use this type of manipulative technique to handle something like this. So let's show you what we're talking about. My example is simple because I want to drive the point home. Y is equal to x. I'm looking over here at x equals 1. And what is the region of this space? But we're looking here at double integration or iterated integrals. This entire exercise has to do with any form of a multiple integral. You can reverse the order of integration. Y equals x. X equals 1. If you look at this point over here, it's a 1 comma 1. You're looking across over here, you have a 1. You're looking here at your origin, you're looking here, you have a 1. If you were to represent this in terms of a double integral, you can either do something with regards to a dy dx, or you can do something with a dx and a dy. You see the order will change based on what you integrate first. Let's look here at one form, dx and a dy. If I want to integrate this with respect to dx first, then I want to integrate this with respect to dy. How do I do it? When I'm doing dx first, I'm looking at my limits along the horizontal dimension. I have a 0 and a 1. My 1 is my upper limit, but the 0 here is going to track along a certain curve or a function. It's y equals x. Since my eventual form is dy, you know here you have to convert your equations into the x equals format. If y is equal to x, x is equal to y, and that becomes my lower limit. And I have a y and a 1. Again, I have an upper limit which is a 1 along the x horizontal dimension. I have a lower limit which is really a 0, but you're going to track up in the dy dimension because we're ending here with a dy, starting with a dx and a dy, but you're going to track along this curve like this. And since you're doing that, you're going to represent your equation in the x equals format. The lower limit is x equals y equals x, x is equal to y. My dy limits will be easy, they're vertical. You're going to track along from 0 to 1, 0 up to 1, and this right here represents your one integral right here. But then you can easily reverse the order of integration and represent it with a dy first, followed by a dx. And how would you do that? In this particular case, when you're doing it, let's erase this. You're looking here from this dimension across here, but you're still looking at the same shaded region. When we're talking about reversing the order of integration, we're not changing our graph by any means. We're still calculating a certain region of space, the area between curves, but we're just changing the order of integrals, dy, dx, dx, dy, or even a third if there was one applicable. Anyhow, how would I do a dy followed by dx? In the dy, you're looking here along from the left to the right. You're looking here and then you're aiming in this direction. You have a lower limit which is 0. It's going to stay across with regards to your dy, but then you're going to track along this curve because your one limit is going in this way, your other limit is going up that way. Since you're going eventually towards the dx, here your equation now must be in the y equals format, and it is y equals x. That'll be your upper limit. And then how do you know what your limits are for your dx integral? You're going from 0 to 1. Now look at these right here. This right here integral should be equal to that. These are double integrals, they should be equal to each other, just your order of integration is different. I have over here a dx followed by dy, I have a dy followed by dx. Pay particular attention to your limits, y and a 1, 0 and a 1, 0 and x and a 0, 1, but these will be equivalent, your end results will be the same, the region of space will be correct. If you were to look here at this, when you're looking here at this part first, you're integrating it, the antiderivative here is an x. You have an upper limit here, 1, lower limit y, you do a 1 minus y. Then it becomes part of your outer integral, which is a dy from a 0 to 1. When you integrate this, you have a y minus y squared over 2, upper limit 1 and a 0. When you integrate this completely, your end result for the area between the curves or region is 1 over 2, and it should be correct. Now let's look here at the other side of the equal sign. We have this other order of integration. Here when I'm looking at it, I have a hidden antiderivative, it's a y. I have a limit x and a 0. When I integrate this, I have a x. But this now is enclosed in your outer integral, which is dx, 0 to 1. When you integrate this, you have a x squared over 2, 1 and a 0, and when you complete it, you have a 1 over 2, and the region of space is the same. It should be equivalent, but the order of integration has been changed. So you're looking here at the gist of it. When you're dealing with multiple integrals, you have something with regards to dx, dy. You can change it from a dy to dx. That simple change or reversing the order of your integration can sometimes get you over and across an obstacle if you're stuck, particularly with those functions which do not have elementary functions. And I alluded to that at the beginning. Something like this, if you're to integrate it, you cannot. There's no elementary function. But let's now look at an example where we can use reversing the order of integration technique to handle that obstacle. This right here is my question. I have an integral 3y to 3 function e exponent x squared dx, dy, and a 0, 1. You're going to do the dx integral first, then you'll do the dy integral second, and let's try to do it. When I'm doing it, I'm looking here at 3y and a 3 and e exponent x squared dx. This right here is my function, but this function has no elementary function, so I'm stuck. I cannot do it. What I want to do is reverse the order of integration such that I'll convert this into something which will be an a, b, my new limits, but I will do a dy first followed by dx. The function will still be the same. We're still looking at the same region of space, but we're going to reverse the order of integration so we can actually handle this, and I'll show you and we will do it. When you're looking at these items here on this side, you're looking here at an equation which is x equals 3y, x equals 3, y equals 0, y equals 1, because this right here represents your first integral where your eventual integral is a dy, and here you would have had to convert these into x equals format. So this right here would be x equals 3y, and then you would have x equals 3. Then that means these ones right here would be y equals 0 and you have y equals 1. These are your limits. Now if you were to graph them out, what do you really have? When you graph them out, we're looking here at x equals 3y, x equals 3, y equals 0, y equals 1. You know this represents your x-axis. This represents a certain horizontal line, y equals 1. X is equal to 3y, x is equal to 3. It's better to just convert this right here into y is equal to x over 3, which you know to be a line, a vertically inclined line, but with a shallow steep, because here the slope is 1 over 3. You can look at it and it would look something like this. Then I have here x equals 3, a vertical line, and it would be right over here. That's what I have. This right here represents in essence what I have over here, but I can start flipping things around to get me into this particular stage, and I can. And how would I do it? When I'm looking here at this particular setup, I'm removing this just for cleanliness. I'm doing a dy first followed by dx. Since we're going from dy to dx, my equations for this a and b should be in the form y is equal to something, because my eventual goal is to go to dx. I'm tracking here from a dy towards a dx, from vertical towards horizontal. I'm looking over here and I'm going in this direction. I'm tracking along this lower limit. My lower limit here is going to track along the x-axis. It will be a 0. My upper limit is going to track along this dashed line going up. But my equations must be in the y equals format. If I have x is equal to 3y, my equation y must be x over 3. This right here will be representing my dy integral. We'll bring in the function at the end. Then I'm going dx. I'm going from a horizontal manner from 0 up to 3, and this becomes my outer limits. You see how things have changed. 0, x over 3, 0 and 3, and my integral has been done. I'm erasing this over here so I can recreate my new integral, and I'll show you what it is. After having done these modifications and reversing the order, I am now looking at 0, x over 3. I have my function e to the x squared, and then I have here a dy, a dx, and my limits 0, 3. Look at the differences between these two integrals. Here's my integral a, here's my integral b, but they're equal. The order of integration has been changed. The limits have somehow changed, but they're equivalent, and you should have the same answer. We can't solve this because there's no elementary function, but we can solve this, and you will see it to be the case. So I've reversed the order of integration by means of understanding how the limits apply and how they change based on if I'm going dx to dy or dy to dx. Equations are x equals format or y equals format. You have to keep all of that in mind, and then you can make the change. And this is what I have, and I can solve it using this order of integration, dy followed by dx. I'm looking here at the inner part. I'm looking at it from 0, x over 3. I have here a function e to the x squared, and then I have a dy. This right here is no different then a constant, you could push it outside because there's no y variable. When you do the antiderivative, you have a y come out, then you have a e to the x squared, which is sitting outside as a constant, then you have a x over 3, and then you have here a 0. Now take this through to completion. What do you have? You'll have a x over 3 minus 0, upper limit, lower limit, the difference of the two. You can pull the 1 over 3 out. I have a 1 over 3, then I'll have an x, e to the x squared will come out. This right here has now become my modified antiderivative. Because it's not complete, we still have a second integral to run through, but this right here is the outcome of this first integral. I have a 1 over 3 x e x squared. That's what I have. Now it's going to come through in terms of my other integral, which is the outside integral. Let's erase this so we can take this to completion. My integral now with the dx is this. I have a 0 and a 3. And you can solve this. How will you solve this? Using u substitution. When we do u substitution, you can say here u is equal to x squared. And then I have here a du is equal to 2x dx. And dx here is equal to du over 2x. You'll have new limits, u1. You put everything 0 and 3 in place of right here, x squared. I'll have a 0. And a u2 will be a 3 squared, which is a 9. This is what I end up having. When I bring it into play, let's complete it over here. What do I have? I have a 1 over 3 sitting outside. I have my u limit 0, 9 because I'm doing u substitution, which is a polynomial substitution technique. I have an x, I have e to the u, I have a du over 2x. These x's will cancel out. This 1 over 2 can come out and make it into a 1 over 6. I'm looking at a 1 over 6, 0, 9, e to the u, du. And we will solve this and we'll take it to completion. When you solve this and take it to completion, you know what it is. It's easy. The antiderivative of e to the u is e to the u. I have a 1 over 6 e to the u. I'm going from 9 and a 0. When I compute this, upper limit, lower limit, the difference of the two, I have a 1 over 6. I have a e to the 9 minus 1 because e to the power 0 is equal to 1, and that right there is our end result, and it will be correct. If someone were to give you this question and you can't solve it because the elementary function does not exist, a double integral, we reverse the order and we've come up over here to our answer, and this will be correct. By reversing the order, I've been able to solve it using u substitution. And it will be correct answer over here, and it will bring us to the end of our video. Before we close out, I'll just show you the gist of what we have done. In this video, generally saying, we had something which looked like this. We were looking at a certain function. We'll call it an f. We are to integrate it first dx, then follow it by a dy, because we were looking at double integrals, and our limits were these. You know what the function was. This video we had function e to the x squared, and it has no elementary function, but this is what we had. What we did was reverse the order of integration such that we kept the function, nothing else changes, but we changed the order. We did from dy to dx. Dx to dy became dy to dx, and obviously the limits changed. I won't use the same letters because the limits kind of changed. How about we just say we had here a prime and we had b prime, c prime. These just represents different values, but this is what we have. And then because of the change in the order of integration, we were suddenly able to do this using what we had, u substitution, and it worked and it came out correct. So this is a technique available. You can use it all the times, but definitely you can use it some of the times when you are indeed looking at multiple integrals, because you need a multiple integral to have a reverse in the order of integration, which will allow you to bypass an obstacle. For a single integral, this technique will not work because for single integrals, you do not change the order of integration. For multiple integrals, you can change the order of integration. That's it for this video. Thank you for watching.